And all right, in 2016, my close collaborator, Jennifer Van Saters, suggested weakened magnetic braking in old solar type stars as a way of explaining some observations of Kepler field stars. And I've spent most of the last 8 years really trying to understand what drives weakened magnetic braking in these stars and in new samples of similar stars. So what I'd like to do today is sort of give you an overview of the both direct and indirect evidence for weakened magnetic braking in old solar type stars. Then I'll discuss 4 key empirical clues for dynamo theorists about how and why this manifests that you should aim to reproduce with simulations. And if I have time at the end, I'll give you sort of a qualitative argument for how this sort of plays out in observations of the sun, for example, where we have a very close-up view. Okay, so the original evidence for weakened magnetic braking came from observations of old field stars with ages measured from astroseismology. And the basic observation was that old stars were spinning faster than you would expect if they continued to spin down over time, like the Skumanich relation, now 50 years old. And it did so in such a way that it deviated from standard spin down earlier in hotter stars and later in cooler stars. So the sort of F-type stars on the right, G-type stars in the middle, and K-type stars on the left, you can see standard spin down predictions is the sort of blue contours, and weakened magnetic braking postulated that at a fixed Rossby number, a single parameter, stars would begin to, basically magnetic braking would shut off, the simplest assumption that you can make. And this idea basically explains this indirect evidence of stalled spin down or weakened magnetic braking in old solar type stars. And this is the most recent work from Jennifer's graduate student, Nick Saunders, just published last year. And the best fit of that critical Rossby number where weakened magnetic braking begins is about 90% of the solar value. So suggesting that our own solar system is already in this weakened magnetic braking regime. Okay. So that's the indirect evidence. And what I've been trying to do is get more direct evidence of how this actually, what's causing this. So the direct evidence has to come from direct measurements of the large scale magnetic field. And the reason for that is the large scale magnetic field, think dipole field, carries most of the angular momentum from the magnetized stellar wind. And spectropolarimetry is the tool of choice to measure large scale magnetic fields. And in fact, for distant stars where we don't have spatial resolution, it's only sensitive to the large scale field. And so you can think of it as a binary test for the presence or absence of that large scale field. So here we're looking at okay, so you have to combine spectropolarimetric measurements of the strength and topology of the magnetic field with some estimate of the mass loss rate, generally from a scaling law with the X-ray luminosity, the basic stellar properties like mass and radius, and the rotation period. When you combine those things, you can estimate for any star where you have all those quantities, the wind breaking torque, or equivalently the angular momentum loss rate, okay? So what we're looking at here is a sample of a dozen stars where we have all of those measurements assembled to be able to make these estimates over the past 5 years using the Large Binocular Telescope and a beautiful spectropolarimeter built by Klaus Strassmayer. And so you can see we're looking, the vertical axis is the wind breaking torque normalized to this star HT 76151 as a function of the Rossby number normalized by the solar value. And the standard spin down model is that a dotted yellow line there would predict this gradual decrease in the wind breaking torque over time. But in fact, what we find in the sample is that at a critical Rossby number, there's a sudden decrease of about an order of magnitude where you find all of these other sun-like stars, including the sun, in fact, and then it continues to decrease beyond there. Down Tau Ceti is more than 2 orders of magnitude weaker. So there's a clear break where weakened magnetic braking appears to kick in from these direct measurements, and empirically, the value of that critical Rossby number is about 90% of the solar value, just as we found from the indirect evidence from rotation. Okay. So that's the overview of the evidence for weakened magnetic braking. And now I'd like to sort of summarize what we think this tells us about stellar dynamos. Because after all, it's this being driven by changes in the magnetic field. So, okay. So first, why should we expect slow rotation to weaken the large-scale field? Well, if we look at the sun as an example, rotation and the Coriolis force and other Reynolds stresses really drives several things that all contribute to the regeneration of the large-scale field. So the Coriolis force, as we saw in Hannah's talk yesterday, contributes to the tilt of bipolar magnetic regions as they emerge. The Coriolis force and other Reynolds stresses also naturally produce both the differential rotation and the meridional circulation. And so as you can imagine that there might be a critical rotation rate where the Coriolis forces are no longer imprinting a significant signature on the convective patterns. And so you're reducing the Joy's law tilt that prevents the differential rotation from separating the leading and trailing polarities over time. And so more of the flux cancels before meridional circulation, which is also weaker, can transport it to the pole and seed the generation of the large scale field. So it's a natural explanation for why we might expect for some critical rotation rate where the large scale field might begin to weaken, as is observed in these older solar type stars. The second clue that we noticed actually almost immediately was that if you look at, this is a plot that you've already seen in Alfio's presentation, the cycle period in years versus the rotation rate, you see that there are a couple of different correlations between those things. But if you look at this series of solar analogs, HD 76151, 18 SCO, alpha Cen A, and 16 SIG, it seems that stars spin down until a critical rotation rate, this critical Rossby number for that given spectral type. But then cycles appear to grow longer and weaker until in 16 SIG, this is a flat activity star. It doesn't have cycles. And so what it seems is that at that critical Rossby number, at that same critical Rossby number where weakened magnetic braking kicks in, cycles are getting longer and weaker over the second half of the main sequence lifetime. And this same pattern appears in both hotter and cooler stars. And that was what allowed us to select our initial sample, looking at these stars that have similar rotation periods, but very different activity levels and cycles or no cycles to try to pin down this behavior. And note that the solar cycle, being in the middle of these two different branches, is a natural feature of our theory, because under this understanding, the sun is already beyond the transition and it is moving upward. The solar cycle is getting longer and we might expect it to disappear sometime in the next couple of billion years. Okay, this is kind of reinforced if you look. The critical Rossby numbers, since activity level and Rossby number are correlated, you can kind of translate the critical Rossby number into a critical activity level for any given star. And if you look at a star with a well-defined cycle like Sigma Draconis that's below that critical value, it shows nice, well-ordered cycles where the minimum corresponds roughly to that critical activity level. But as stars age and their average activity level decreases over time, you get a case like HD 16620, which is the only the first confirmed Maunder minimum star where it had cycles during the Mount Wilson survey, but then since then has shown 20 years of constant activity. So it's gone into hibernation. And its critical activity level is there at about its average activity level. So it's evolving. You might expect that as stars evolve through this critical activity level, the cycles can become intermittent, and you see these effects like grand minima. But then eventually, evolving towards subgiant phase like 31 Aquila, the average activity level eventually gets so far below that critical level that even the most extreme active regions that are like anti-joy or anti-hail cannot kick it, the dynamo between the cycling and non-cycling phases. So it's too far below for even the most extreme events to do that. And you go into a permanently flat activity phase that we see in a lot of these old solar type stars in the Mount Wilson survey. The last clue is super exciting because it's a really direct test of this idea. In 2020, we found this star 94 Aquarius AA. It's a subgiant with a very clear cycle. And when we tried to model the rotational evolution, we found that it was in this very special evolutionary state just before ascending the red giant branch. So the idea here is that, that 94 Aquarius A, had a cycle probably when it was evolving in the first couple of billion years, but it hit the critical Rossby number. It parked at that critical Rossby number until physical expansion pushed it over the critical Rossby number and made the cycle disappear. But then later in the subgiant phase, it has a structural rebalancing where the envelope expands and the core contracts. You get the deeper convection zone basically overwhelms the longer rotation period from the physical expansion to increase the convective turnover time. So you can actually dip back below that critical Rossby number once again, briefly before ascending the red giant branch. And lo and behold, we find it there and it now has a cycle again, right? So you can think of the onset of weakened magnetic braking at this critical Rossby number. That's the same critical Rossby number that defines where there are clear activity cycles below and flat activity stars above. Okay, so those are the 4 clues that I would like to see more people try to reproduce with dynamo simulations. These are great constraints for models. Okay, how much time do I have? Okay, so I have time to do one of this. So I mentioned how slow rotation might gradually decrease the strength of the large scale field. It also affects the other side of the dynamo loop, which is flux emergence. So if you have a large scale field, differential rotation will wrap it up and create buoyant magnetic loops at the base of the convection zone that emerge as new flux. Well, if the large scale field is weaker and the differential rotation is weaker, you might expect less flux to emerge. And so it's a downward spiral. You've got a weaker large scale magnetic field. It creates weaker flux emergence. You have less flux to create more large scale field, and it just is a downward spiral. So there's a secondary effect that we've seen evidence for in our spectropolarimetry, that it's not just the change in the morphology of the magnetic field. There are secondary effects on the mass loss rate. And we can understand that as also like a side effect of the topology change that we see play out in our own solar system over the course of the solar cycle. Because mass loss goes along open magnetic field lines, and the amount of open magnetic field lines changes over the course of the solar cycle and on stellar evolutionary timescales as well. And so basically more complex field throttles the stellar wind. And so you can basically reduce the mass loss rate beyond what is expected in traditional models to further decrease the angular momentum loss rate, okay? So it's both change in magnetic morphology and a change induced change in the mass loss rate that is causing the weakened magnetic braking. Okay, and with that, I will put up my summary of conclusions. These are the 4 clues that dynamo modelers should try to reproduce with simulations if they want to reproduce this kind of behavior that we're seeing in old solar type stars. Thank you very much.
Thank you, Travis. Questions? There's one there.
So Travis, love this stuff, you know. So would the young sun have had a greater or lesser mass loss rate, given the scaling relation you just noted?
The young sun would have a much greater mass loss rate, yeah.
Good.
Although a very young sun also has a complex magnetic field, right? And so there will be some throttling in the early times, and this is what creates the persistent fast rotating sequence in young clusters, for example, right?
Thanks, Travis. So you now clearly have no problem in slowing down or breaking stars. What are the observational constraints that would be able to tell sort of the proportion which is due to the mass loss, which is due to the cycle changes?
We can actually estimate that, and we have in each of our papers over the last 5 years, just from the models, you can attribute, just by comparing different stars at different evolutionary states, you can just change one parameter at a time between those models to try to attribute how much is due to the mass loss rate change, how much is due to the topology change. And so early on, this is like 50-50, like about half mass loss rate changes that are beyond what's expected and about half from topology changes that were previously unexpected. Later, it gets dominated by the morphology changes.
Hey, Travis, so there are 2 other very independent observations from the sun as a star context, which really adds up to this and complements this. One is this observation by the Max Planck group, which shows that the sun is comparatively much more inactive compared to stars which are of similar age to the sun. The other is a work by Ilya Ususkin, who shows that if we look at the long-term solar cycle activity, that is kind of oscillates between 2 phases, inactive monominima-like phase and a regular activity phase. And if you put that together with your observations, all of this suggests that the solar dynamo right now at this point in time is perhaps in a subcritical regime where it is transitioning between an active phase to inactive phase, but right now has access to both of these phases. And we wrote a paper in 2021, I think, in MNRAS, explaining how this can happen if we change the Rossby number and add noise to the system. And that sort of beautifully explains all these different observations nicely. So perhaps you could have a look at the paper.
Yeah, I'm definitely familiar with that paper. It is one of our inspirations for kind of bringing all of these clues together and putting it all together into this picture. One thing I'll say about the Max Planck result about the sun being unusually inactive for its age, if you control carefully for metallicity and temperature in that sample, that turns out not to be the case. I think subsequent studies have shown that the sun is perfectly normal for other stars in its same situation. Those other stars are also in the weakened magnetic braking regime, probably, right? So I don't think that is a signature of the subcritical dynamo. But the other part, I definitely agree. Yeah.
I have a question and one comment, Travis. So my comment is there are 3D numerical simulations since 2020 or something like this from different groups, and all of them kind of show that when the star rotates very slow, the dynamo changes from cycling to steady. This will fit your theory. And the second, or my comment is, have you calibrated your Rossby number with metallicity, like for example, Alfio did, because this could change the results or not?
Yeah, absolutely. As Alfio mentioned, we've been working together to try to improve the astroseismic calibration of the stellar Rossby number in a sample that is diverse in metallicity, temperature, surface gravity, all those things that might also matter. So that's an effort that's just beginning and but is definitely important.
Travis, I have two questions. Thanks for the talk, interesting results. And first, not very clear why you relate mass loss with X-ray activity, because X-ray comes from closed loops, not open magnetic field. So it should be opposite relation.
Yeah, so the reason for that is, so it's based on Brian Wood's work, where there are, for a few dozen stars, direct measurements of the mass loss rate, well, let's say direct modeling of the inferences of the mass loss rate from Lyman alpha observations, and you get asymmetries where you can actually model the mass loss rate from very nearby stars. And in that sample, there's an empirical correlation between the mass loss rate and the X-ray flux per unit surface area. There is a lot of scatter around that relation, and that's another area where there could definitely be improvement. Yeah, but direct mass loss rates are possible for nearby stars, and we're working on that as well.
And my second question is that if you look at the sun, solar rotation, then solar core rotates uniformly, and the differential rotation only in the convective envelope, and dynamo works only in convective envelope. So it seems that magnetic braking should be related to some primordial magnetic field that involves the radiative interior, not just to dynamo.
Yeah, possibly. I think that in the solar case, like it's very clear that the sun still has differential rotation, still has a lot of the ingredients that we expect to drive a dynamo. The question is like, how does the present state of the sun compare to how the sun was just a billion years ago? The sun was probably not in the weakened magnetic braking regime. And the issue is that the wind braking torque of that earlier sun is predicted to be about 10 times stronger than it is at the present day. So yeah, that's an interesting question. Yeah.
There is one online question, so Emre.
Yeah, I have just a comment on Dibiando's question and remark and Travis's reaction to that about the Max Planck results. I was not in that study, but I was, yeah. So we can also, that those super active solar analogs, even though some of them have very similar metallicities, the thing is that they form only a subsample of the entire sample, and because they are periodic stars, so to say, in the sample, the non-periodics are a bulk of the distribution. So the majority of the stars in the sample are non-periodic, and the sun is also non-periodic. So one has to compare the sun with the with these non-periodics as well. And when one does so, then these super active, like high variability solar-like stars are maybe outliers. That's also a possibility. That's what I want to say. And the question why is, yeah, maybe different patterns of magnetic flux emergence or whatever. This is still a riddle. Yeah. Thanks.
More questions? Okay, so thanks, Travis, again.